Hi, my name is Jordan Stevens, and this is my part 2 of the project, an explanation of my implementation of my neural network. First, I'm going to go into my concept map. This was the relative one that I showed in the last video. That just shows that I have 12 input variables and 1 output variable. The output variable is a logistic variable where it's either 1 or 0. Now I'm going to go into explanation of all of these input variables. The first two are the x-coordinate and the y-coordinate, and they're based on a 9x9 grid that was shown in the paper. The 9x9 grid is just the relative areas of the national park. It's just an easy way to show geographical areas of the park and which ones might be more likely to have fires, because some areas are more likely to have fires than others because they have certain conditions like wind speed and stuff like that. Next input variables are the month and day are used because fires are more prevalent in certain months like August and July, especially in the Northwest. The day is also very important because of weekdays versus weekends. Since human negligence is a large cause for forest fires, people are more likely to visit on weekends, then there's also a higher chance of fires on weekends than weekdays. The next three variables are the rain, wind, and temp variables. They're pretty self-explanatory. They all directly relate. They're all directly related to forest fires. How they were measured was rain was measured on a 30-minute interval and averaged over the course of a day by the staff of the park. Wind and temp were gathered from recent meteorological weather forecasts for the area. The RH variable is the relative humidity, which is measured by the percentage of water vapor in the air until the saturation point, where 100% is where water vapor reached the saturation point. That is also gathered from a local weather forecast. The remaining four variables are related to the FWI, which is the Canadian Fire Weather Index. And this has four variables that are associated with it. The FFMC, which is the Fine Fuel Moisture Code. It's a rating of the moisture content in fine fuels. These are things that will easily start fires. These are the igniters of fires. So this is directly related to how easy a fire could start. The DMC, or the Duff Moisture Code, is a rating of moisture content in medium pieces of organic material that will serve as the initial fuel for a fire. So you not only need a spark, but you need fuel in the relative near region to actually get a fire going. And then there's the DC, which is the Drought Code, which is a rating of deep moisture content in large pieces of wood like logs, which serve as a big source of fuel for a fire's longevity. So this, in a lot of larger fires, there's a low drought code, and this is like the fuel that'll make a fire really big and spread a lot. And then there's the ISI, which is the initial spread index, which is a rating that takes into account the three ratings above and the average wind speed. This rating gives a good indication of how fast the fire will spread. These are all very important in the prediction of fire. All three of these directly relate to how easily a fire can start and how big the fire can actually get. Next is my output variable explanation. The fire's output variable is the only output variable, and it is determined based on the input variables, whether there will be a fire or not. Since there are only two options, there is a fire and there is not a fire, I will choose logistic regression as the modeling parameter in the neural networks. The output of the test value will be a numeric value between 0 and 1, which will be directly correlated to how likely a fire would be, the probability. After this, I will come up with a decision statement that will decide based on percentage whether a fire will happen or not. Next, I'm going to go into my MATLAB implementation. I'm going to use the NN Start tool, GUI, and form fitting tool to fit the form of a regression curve. I am first going to normalize the data, since most of the time it helps neural networks find the appropriate weights for the nodes. Once I do this, then I'll enter the input and target value into the neural network and analyze the output. So I'm going to go into how I normalize the data. So this data I found, I have 518 values currently. These are all the values that I just explained, the input variables right here, and the fire variable, which is that logistic operator. I gathered more material and more data from the website than the actual paper did. I actually gathered days, which that's where the 0 comes in. The 0 is when there's days when there weren't fire in an area, and 1's when there's a fire in the area. So after this, I normalized it. This is the normalized value, which is a value between 0 and 1. And then over here is a test set I came up to randomly test the accuracy of the actual program. So now I am going to go into MATLAB. This first is just to initialize variables. This is a pretty easy thing to do. All I did was just go to Home, Import Variables. I selected my project data, which is a CSV file, opened it, and it should load up pretty quick. This basically is just finding all the values in a Excel file and putting them here. I do not know why it's taking so long. But anyways, once we do that, yeah, here it is. It's just the data. And then I can generate a script, and I just copy and pasted the script and put it right here, which will import the data properly. After this, these two lines are important. This is the input and target values. So once I did this, I put over here, I put NN start, which comes up with a GUI for neural networks. I went to the fitting app. I went to next. I decided that my input was my input and that my target was my target. After this, I decided how many hidden neurons I want. I found after a lot of testing that 30 seems like the best option for me. Once I did that, I decided to train my data, and I used Levin-Ribbon-Cart. Once you train, the real thing you should look at is regression. This tells you how correlated it is. These values are kind of low. So after I train the data more, so you can train the data more and more times until you reach a training data that you want. So after this, I went to next, and then you can actually have a simple script of this. So that's what I did, is I copied and pasted a simple script, put it below here. This is the simple script, which calls upon the neural network. So I'll run this. Now, one of the bad things about a neural network is that it takes a little bit of time to actually run it and for the nodes to actually get the weights compared to other methods. So I'm going to stop my video and come back whenever it's done. Hi, I'm back after it was done loading, and here's my regression model that I have printed up. As you can see, the R value is really low, which is a sign that there's something wrong with our either input data or output data, or the actual fundamental way that the neural network works. If I go back to my PowerPoint, I'm going to show you, well, training data was pretty easy, just normalizing it. Then I went into just a random test of 8 values, seeing its accuracy, not just based on the regression model. And each one of these values is a percentage from 0 to 1. So the first one has a 92% chance that it is a fire. And out of all of these, I put a 75% threshold for whether it's a fire or not, and only one value failed, which is the fourth value here. So this is the only one that failed out of the 8 values. After that, I went into, this is the highest R value that I could get out of finessing it. So that means there were some problems with our model. The first most glaring problem with our model is that the model uses a linear line instead of a sigmoid for a logistic problem. this will add to error and add to not being accurate. Another reason is that the data I might have chosen for the days without fire might be too close to the data that has fire. So that means that if there's not much difference, which you can kind of see right here, not much difference, then there might need to be like problems like days that are a little bit further away from that to balance it out. After looking at this and after figuring it out, I actually found a function, the GRNN, which is the Generalized Regression Neural Network, which accommodates for a sigmoid instead of a linear line. This leads to errors stemming from the data that's too close rather than the linear line. So basically, I use this method. I think it's right here. Yeah. So I use this method, and I was still getting a very large errors, which I will show you right here. So this is the This is the function that I put at the bottom right here. This is just the function I used for it. So if I type in prob, it was still not doing very well. The values that this is based on that test set that the first 4 were fires and the last 4 were not fires. This isn't giving very good probabilities either. So I would bet that the problem was either not enough data or the data was too close. So, in conclusion, I believe there is a way to accurately predict probability of forest fires based on variables given. I believe that more data given for the problem will result in a more accurate model. I also believe that a GRNN model would be a better predicting model than a form-fitting model based on the logic of sigmoid and logistic regression problems. And here are my references for the paper that I used, the data literature review, and the site that I found all the rest of the data for days that did not have fires. I want to thank you, and have a great day.